First of all, let me welcome everyone to the School of Physics, guests, colleagues, friends. It's with the greatest pleasure that I welcome you to the presentation of the Robert Street Doctoral Prize in Physics. The award of the second Professor Street Prize is also tinged with a little sadness. As I'm sure most of you know, Robert passed away on the 4th of July this year. The school was represented at the funeral by Associate Professor Joan, and we were indeed honoured to be able to reflect on Robert's life on that occasion. So thank you very much for the family for letting us to do that. At this stage, I'm sure Bob would ask me to get on with it. So once again, I'm delighted to welcome Robert's daughter, Associate Professor Alison Street, AO, and her partner, John Barclay. Shortly, I'll ask Alison to make the presentation. We're videoing today's presentation so that Alison and the Street family can have a record of today's proceedings. I'd also like to welcome Xingqiu Cheng, who's the recipient of the Robert Street Doctoral Prize. So welcome. The Doctoral Prize in Physics, of course, is made possible through a generous bequest to the School of Physics by the late Professor Robert Street and his wife Joan. And from the outset, I'd just like to thank the Street family for the generosity. I know that Joan remembers her time here with Bob with great affection and fondness. And of course we do too. So the occasion will proceed as follows. First I want to provide a little background information on the late Professor Street. I'll then read out the nomination for Dr Changxi Zheng and ask Alison to present the award. Alison would like to say a few words on behalf of the family, and after that we will invite Changxi to make a presentation on the work that led to his award. After some photographs, we'll have afternoon tea served in the foyer. So let me begin. Professor Robert Street, BSc, PhD, DSc, Honorary DSCs, Fellow of the Australian Academy of Sciences, Fellow of the Australian Institute of Physics, Officer of Australia. So Robert Street was born on the 16th of December 1920 in Wakefield in Yorkshire, United Kingdom. In 1941 he received a Bachelor of Science from the University of London, actually taking the degree in Bristol due to the bombing of London at that time. He began his career during World War II working at the Air Defence Research and Development Establishment, researching absolute measurement of power. In 1944 and 48 respectively, he received an MSc in the relatively new area of wave mechanics and a PhD on absolute measurement of power. After the end of World War II, Professor Street was appointed as an assistant lecturer in physics at the University of Nottingham. In 1954, he became a senior lecturer at Sheffield University, and in 1960, Professor Street moved to Australia with his family to become the Foundation Professor of Physics at Monash University. In 1966, he earned a DSc from the University of London. In 1973, he was elected to the Australian Academy of Sciences. In 1974, he was appointed as Director of the Research School of Physical Sciences at the Australian National University. And from 1978 until his retirement in 1986, Professor Street was Vice-Chancellor of the University of Western Australia. However, this bare-bones summary does not do justice to a remarkable man and a remarkable career. It was my pleasure to have been taught by Professor Street in the early 70s and experienced firsthand the obvious joy he had for physics, especially experimental physics. This is a man who was passionate about teaching and passionate about research, and that came across very, very clearly to all students. I could give you many anecdotes of the things he did, went out of his way to engage with students, an absolute role model for academics today. Robert's practical bent derives from his earliest years and possibly from having been the son and grandson of coal miners. His father was his role model, and Robert reflects that we built all sorts of things, including crystal wireless sets and valve sets. In those days, our houses had gas but no electricity, and the valve sets had to be driven by great accumulators, lead-acid cells, with 120-volt dry batteries for the high voltage. The soldering was done with a soldering iron, which quite often was heated by gas, or in an emergency, you could stick it into the kitchen fire to heat it up. Robert says, "I've always thought that in almost any endeavour, if you can discover things for yourself, even though they've already been known for many years, this is a real encouragement to continue." The young Robert Street, even at age 12, had an ambition to pursue a career in physics, deriving encouragement from an inspiring teacher. This must have been a truly inspiring teacher, because Robert's stated aim at age 12 was to become a professor of physics. Although Robert won an exhibition to Oxford, he was ultimately not admitted because he did not fulfil the Latin requirement. The classics were not taught at his preliminary school. In Robert's own words, "My translation from Latin into English of a troop of Roman soldiers crossing a river disguised as lilies," that was a bit unreal. He reflected his capacity to translate was somewhat diminished by his lack of preparation. Instead, Robert started at King's College, London in 1940, but not in the Strand, but in Bristol. Because of the bombing, King's College had been evacuated from London to Bristol, just when Bristol itself was about to become a bombing target. During his time at Bristol, Robert met his wife Joan. In fact, he met her during an air raid. Joan was studying history at King's College, and during the war she worked at Bletchley Park, where the Foreign Office had its code-breaking operations made very famous in people like Turing and so forth, the Enigma machine. Robert was told that he was not to ask his wife what she did, and he said he never did and she never told him. During the war, Robert was interviewed by none other than C.P. Snow for a position at the Air Defence Research and Development Establishment in Christchurch on the southeast coast of England. When he got there, the chief superintendent was J.G. Cockcroft, later to be Nobel Prize winner. He won the Nobel Prize in 1951 for his work in nuclear physics. Robert worked in the basic research group led by Charles Oakley, who developed the first commercial scanning electron microscope. He worked on radar and developed techniques for measuring the power output of signal generators used to calibrate the receivers that were incorporated into the radar sets of all kinds. It was during his wartime work that Robert became interested in solid-state physics. To quote from Robert, "An essential part of the whole radar system were the crystals. The crystals were the wire contact. Without these, it would have been impossible to get the sensitivity you require for centrometric radars." His interest in solid-state physics led him to do an MSc in his spare time on wave mechanics through London University in 1944. Remarkably, Robert came very close to developing a transistor. In his characteristically modest way, Robert recalls, "If I'd understood the wave mechanics business of the point contacts, just maybe in a million years, I would have thought about putting two wires onto that crystal to see whether the current through one affected the current through the other." Nowadays, it seems such an obvious thing to do, and they did at Bell Telephone Labs do in fact that, to produce the point contact transistor. After the war, Robert extended this work using wartime equipment, including Oliphant's famous VFO7 klystron, the VFO standing for valve for Oliphant. The work led to Robert's PhD thesis obtained from the University of Nottingham. Robert was appointed assistant lecturer in physics at University College, Nottingham, and began investigating the effects of magnetic fields on the mechanical properties of magnetic materials. This led to a lifelong obsession with studying and trying to understand the time dependence of magnetization, because in Robert's words, it tells you quite a lot about what's going on inside a magnetic material, and time dependence occurs in all sorts of ways in all kinds of systems. Other people working in the field of magnetism with whom Robert interacted included Lord Patrick Blackett and Louis Niel, both who were awarded Nobel Prizes in physics, although Blackett's was for cosmic ray research, not magnetism. In 1954, Robert took up the position of senior lecturer at Sheffield University, where he made a series of low-temperature studies that required the building of a hydrogen liquefier. Yes, liquid hydrogen. Later, of course, at Monash, he established a liquid helium plant, a much safer option. In Robert's words, "We had no hydrogen detectors. It's always seemed to me a great tribute to the people who made the joints in all the piping that they didn't leak hydrogen. Because if they had leaked, I'm sure I wouldn't be here now, and nor would half the university. There would have been a rather large explosion." After several years at 2 universities in England and having produced some landmark papers on magnetism, in 1960 Robert and his family moved to Australia. Robert taking up the foundation chair of physics at Monash University. Robert attended an interview in Manchester, just over the hill from Sheffield. Robert reflects that the interview started off extremely well, even though Louis Matheson, the newly appointed Vice-Chancellor of Monash University, appeared for the interview late, and he was dressed in cricket flannels because he had just got away from a cricket match where he'd been batting. Things don't happen like that anymore. It turned out that Louis Matheson was a charismatic person filled with the fire of doing something very much worthwhile in building a university from scratch. Talking to him, I found it an extremely appealing proposition, but it was a tremendous leap for me and my family. Australia was unknown to me beyond the image and the example that Matheson was projecting. The world of the early 1960s was very different to today. Robert notes that, strange as it seems now, all you had to do was ask. So I asked for all sorts of things: a helium liquefier to avoid the possibility of blowing ourselves up with hydrogen, electron microscopes, magnets of all kinds, equipment to put in our laboratories, lecture theatres. All these things and more were in abundance. We just had to ask. It was very easy. Oh, how I envy that. At Monash, Robert was involved in an enormous number of activities. In addition to his teaching, research and administration, he was involved in science education through the development of the Victorian physics curriculum, science communication through the ABC. I just want to say that I've got a booklet from 1960, was it 62? Where Robert and Bill Rackinger were television stars doing hardcore, not popular, but hardcore physics for the ABC. A whole series of lectures in 1962. We think they were very modern in doing, distance education online. This is 1962. And what really strikes me reading through the curriculum is that you didn't shy away from doing real physics. You wouldn't get away with that today, Bill. So he also did work through the Atomic Energy Commission, the National Standards Commission. That Robert was pivotal in bringing the metric system to Australia. He worked for the ARGC, which is the precursor to the ARC, and this list is by no means exhaustive. I should also point out that whilst on the ARGC, the precursor to the ARC, Monash did extremely well in grants. There's a strong correlation, but not causation, between representation and grant outcomes. This is something we're going to be looking to in the future. So he did a large number of things, and he said, when you're interested in things, you just do them. That's really what was happening. Following his time at Monash in 1974, Robert took up the directorship of the Research School of Physical Sciences at the Australian National University. Under Robert's leadership, the Anglo-Australian Telescope was established. This had a somewhat troubled history, details of which could take up the entire talk. The AAT was officially opened at Mount Siding Spring in 1975 by Prince Charles. Following his time at the ANU, in 1978, Robert took up the position of Vice-Chancellor at the University of Western Australia. He retired in 1986, but whilst as Vice-Chancellor, he would quickly read Physical Review letters and other journals before passing them on to his colleagues. Therefore, he was able to keep abreast of developments. And remarkably, following his retirement as Vice-Chancellor from UWA, he started a completely new chapter in his scientific career. He returned to the laboratory, taking measurements. This is probably unique for a Vice-Chancellor and testifies to Robert's curiosity and genuine interest in science. In 1988, he set up a magnetics laboratory at UWA. He published papers, supervised students and postdocs, wrote and attracted ARC grants, produced patents. He became a member of one of Australia's earliest nanotechnology companies, Advanced Powder Technology. Since he retired, he had supervised, since retirement, 17 PhD students, published 125 refereed high-impact publications, including papers in Nature, in companies in a wide range of areas, with multiple papers attracting 100 or 200 citations, to say nothing of the other outputs, which I think is not a bad record for a retiree. Robert received numerous awards, including honorary DSCs, Fellowship of the Australian Academy of Sciences. In 1985, he was made an Officer of Australia for his contributions to education and research. In 2011, we were fortunate to have Robert join us for the 50th anniversary of teaching research in physics at Monash. We took Robert on a tour of the Australian synchrotron. It was really remarkable to see how many interesting and probing questions he asked of the young scientists. He went round every single beamline. People a lot younger than him were rather exhausted and wondering when we were going to stop the tour. And he asked question after question. He really relished being back in an experimental facility. It was also interesting to see how he engaged with young scientists. He clearly had the capacity to interact in such a natural and engaging way, inspiring the next, or perhaps the next to next generation of scientists. The quote from Robert: "Someone has said that this life in science is rather a childlike existence. I think it is, and as soon as you lose the idea of wonder at very simple things happening to you, you may as well go and be a grumpy old man somewhere else." So this is a very short overview of the career of Professor Robert Street, known affectionately to staff and students simply as Bob. It doesn't do justice to a remarkable man and a stellar career. Bob was an inspiration to us at Monash in the 1960s and 70s. I hope that the award named in his honour will be an inspiration to future generations of physicists at Monash. So after that brief overview of Bob's career, let me just say a little bit about Alison, Professor Alison Street, Bob's daughter. It's of course a great pleasure to welcome you once again to the presentation of the award named after your father. Alison has had an illustrious career in hemostasis and thrombosis at the Alfred Hospital. Now she's an honorary there. She was Vice President Medical of the World Federation of Haemophilia and was actively involved in haemophilia on the international stage. She received an AO in 2005 for services to medicine and has been a chief examiner for the College of Pathologists, actively involved in the College of Physicians. It was the greatest pleasure and humility that I asked Robert's daughter, Professor Alison Street, to come forward to make the award to the Robert Street Doctoral Prize winner for 2013, Dr Changxi Zheng. So Dr Changxi Cheng joined the School of Physics in 2008 to pursue a PhD degree in experimental condensed matter physics, so it's entirely appropriate given that solid-state physics was Bob's passion. He conducted this PhD under the supervision of Professor David Jessen. During his PhD, he developed a molecular beam epitaxy and surface electron microscopy technique that was capable of both growing and simultaneously imaging and studying semiconductors, particularly gallium on gallium arsenide. Research carried out during his PhD led to 9 papers, including 1 in Physical Review Letters, 3 in Applied Physics Letters, and papers in the Proceedings of the Royal Society, Ultramicroscopy, and the IBM Journal of Research and Development. Changxi was awarded the degree of Doctor of Philosophy in 2012 with flawless examiner's reports. In the same year, he received the Chinese Government Award for Outstanding Chinese Students. His work has also been recognized in the Best Poster Award at the 35th Annual Condensed Matter and Materials meeting in 2011. Currently, Dr. Zheng is working as a research fellow in the group of Australian laureate fellow Professor Michael Feurer. His research focuses on developing nanodevices based on 2D materials, such as graphene, molybdenum disulfide, and tungsten disulfide. In 2013, Changxi was awarded the highly competitive Discovery Early Career Researcher Award, or DECRA, from the Australian Research Council. It is therefore with great pleasure that I ask Alison to formally present the award to Changxi.
Well, Michael, thank you very much indeed. John and I are delighted to be with you all today. And first, my many congratulations to Xingqiu Cheng on winning this award. I do hope this recognition and celebration encourages and assists the progress of your scientific career, which I'm sure will be a most successful one. We're looking forward to your presentation. As you know, Dad died in July, and on behalf of my family, I should like to thank sincerely all members of the physics and wider Monash community for their many tributes and support at this time. John Cashin represented the department at Dad's memorial service. John, you spoke most eloquently, and we were very grateful for your presence and contribution. Mum still has many happy memories of their days at Monash, and we'll be sharing today's programme content, including a video, with her when we travel back to Western Australia next week. I read a short poem at Dad's memorial service, which I think is equally appropriate to today's occasion in celebrating enthusiasm for scientific discovery. I sourced it from the internet. As you know, my father was a humanist rather than a religious man, so we had a very eclectic series of readings and contributions at his memorial service. This was a winner in an international poetry competition conducted in 2001. It's an ongoing thing, it's done annually. But this was the 2001 event conducted through the Science Education Review by science teachers. It was written by a primary school student called Adele O'Driscoll. She at the time was a student in Rockhampton, and it's called I Want to Be a Scientist, which I hope you can relate to and enjoy. I know that Dad certainly would have done so. So what Adele wrote was, I want to be a scientist. I want to be a scientist. I want to own a lab. I want to be a specialist. You might think I'm mad. I want to use a laser beam. I want to win awards. I want to measure gravity and study different laws. I don't want to be a circus clown. I don't want to be a nurse. I don't want to be an undertaker and drive round in a hearse. I don't want to be a fireman and battle fires all day. I want to be a scientist of today. So many congratulations again, Changxi, on winning this award, and thank you all very much.
So the title of my presentation is Low Energy Electron Microscopy, Making Movies at Nanoscale. And actually here are the movies I take from the facility, and I will show you details in the presentation. So first of all, I would like to thank Professor Robert Street, who set up this award, and this gives me the very nice opportunity to present my PhD work. So the materials studied in my PhD is 3-5 semiconductor materials. So what is 3-5 semiconductor materials? And this is materials are compound semiconductor formed by group 3 and then group 5 elements. So the outstanding members of this group material is gallium arsenide and aluminum arsenide. And these materials are very important in our society because they have excellent physical property. For example, they have direct band gap, and which is well suitable for making optical devices. Also, they have high electron mobility. For example, the gallium arsenide electron mobility can go up to 8,500 at 300 Kelvin. And this is well suitable for making high-speed electronics as well. So due to this is excellent materials property, gallium arsenide chips are widely used in our daily life. For example, the laser pointer and barcode reader, and also the CD player, satellite mobile phone as well. So due to the importance of the gallium arsenide devices, the 3 people were awarded the 2000 Nobel Prize in Physics for their contribution to developing semiconductor heterostructure used in high-speed and optoelectronics. In addition to this is technological applications, gallium arsenide devices also have important scientific application. For the 3 people here were awarded 1998 Nobel Prize in Physics for their discovery of fractional quantum Hall effect. And the discovery was obtained from gallium arsenide devices. This is because gallium arsenide devices has the high mobility. So the central component of gallium arsenide devices is the layer structure, which is shown here. In physics, we call this is layer structure is heterostructure or quantum well interior structures, and similar to the the layer hamburgers in our daily life. But the difference between the hamburger and this is layer structures is the scale. As you can see here, the scale bar show up is the 20 nanometers. It means that the thickness of the layer is around 10 nanometers. And so how small it is. As we know, a nanometer is around 75,000 times smaller than the diameters of human hair. So it's really thin, this is structure. So how do we make these thin structures? Molecular beam epitaxy system is widely used. What is molecular beam epitaxy system? Schematically, it can show here. It's quite simple. It's just like a cooker. First of all, you need to heat up the effusion cells to evaporate materials to ultra high vacuum. And this is evaporated material will deposit on the flat substrate and form thin layers. It's just like the deposition of water layer on a mirror in the bathroom. Schematically, the system is really simple, but actually the real system is really complicated, as you can see here. And this is one of the molecular beam epitaxy systems used in other people's lab. So as we know, the drugs, the sauce or the cooking time is really important to make a yummy dish. So in materials growth is the same. But we need, in order to grow high quality materials, we need to adjust lots of parameters. For example, the growth temperature, and the growth rate, and also the materials ratio. And this plot gives us the information is that people have a long time striving in making high quality gallium arsenide devices. As you can see that in the 10 years, and then the mobility increase of the gallium arsenide devices increase a lot. So the main difficulty to make high quality gallium arsenide materials for device is due to the ambiguous growth mechanism. This ambiguous growth mechanism is mainly because we are lacking because the lack of real time and real space growth information. So understand the growth mechanism requires real-time and real space information. And to obtain the real-time and real space information is the goal of my PhD research. So in order to obtain those critical information, and the facility I use in my PhD study is low energy electron microscopy, LEEM. So what is LEEM? In LEEM, we use low energy electron for lighting. As you can see the photos here. The electron beam is come out of the electron column, as you can show here, and then diffracted by the magnetic prism, and then come to the sample surface, and then reflect back from the sample surface and taking the the information of the surface, and then diffracted by the magnetic prism again, and then form the image of the surface in the imaging column. So the advantage of these techniques is that it allows real-time non-destructive observation of the growth process at high resolution, for example, the 4 nanometer laterally and atomic height vertically. So here is the LEEM, and in order to study the gallium arsenide system, and I developed a lot of things based on the commercial facility, which is shown in here. As you can see, it's really complicated. So I don't want to give you all the details about the designing. But I would like to say is that I learned a lot from this experiment setup development. So with this experimental setup, and then we can use it to study the gallium growth mechanism on gallium arsenide surface. So first of all, what we study is that we heat up the gallium arsenide substrate at high temperature. And then at high temperature, the surface will decompose into arsenic and gallium. And then we'll form droplet of gallium on the surface. And using them, we can take the movie of this whole process. And this movie is taken by the former group members, and the result is published in the renowned journal Science, as you can see here. Here, as you can see, and this is black dot gallium droplet. With the heating go by, and the droplet will grow up. And when the droplet grow up to some certain size, it will move across the surface along certain crystal directions and create a trail. So as I mentioned, with this facility, we can observe the whole process happen on the surface. So therefore, I use this facility to observe the droplet coalescence on the surface. So what is coalescence? It means that the two droplets contact to each other and then form one droplet. And in gallium arsenide system, what we find is that the coalescence happen on the surface is asymmetric. And so what is asymmetry is that the small droplet would move to the big droplet and form one droplet. And this behavior is different from water droplet on the glass substrate. And for the glass substrate, and then the two droplets will move to each other and form one droplet. But for gallium, is that only the small droplet move to the big droplet. So the big droplet doesn't move. So with LIM, and then we can understand the physics of the droplet dynamics. Therefore, based on this understanding, we can control this tiny droplet. As you can see here, what I do to control the droplet is that I expose the droplet under an arsenic flask. And by adjusting the temperature, first the droplet will be stabilized both in position and the size. And when the droplet size, when the arsenic flask is open, and then the droplet under the arsenic flask will move across some distance, also its size will decrease. And once we stop the arsenic, and then the droplet will recover to stable again. And this line shows up the decrease of the droplet size during the whole process. So with this droplet, and then we also can react with arsenic and then form nanostructures. And people have done lots of work on here and then formed various kind of nanostructure. And here is one of the example, which is the gallium arsenide quantum ring. As you can see, it has the two rings of the thesis structure. So with LIM, we also can take the movie and then to understand the whole process. Since this process is before this study is still under controversy. So as you can see here is the images taken from the movie at different stage. First is as a gallium droplet here, and then when the arsenic is open, and then there will form a skirt outside the droplet, and with the reaction further going, and then it will form the structures. The skirt will become much more clear, and also it will form the ring structure in the center. So with this LIM, and then we can stop the reaction at various and different stage, and then take the sample out, and then use atomic force microscope to scan the morphology of the nanostructure, which is shows here. And also with the NIME profile, we then can build up the schematics of the whole process, as you can see here. So what we think by this is information, and then we can build up the model for the reaction, and as well as the formation of the nanostructures. And here is the series, so I wouldn't give you too much details about this. And then, but we can build with this theory, and then we can recover and build up the growth mechanism model, which is shows here. And the blue line here represents the droplet. And with the arsenic reaction, and then we can see that it will form the structure is the outer ring and the inner ring. And with this model, and then what we can do is that we know the outer ring is due to the reaction diffusion, and the inner ring is due to the reactive wetting of the droplet at high temperature. So in the previous slides, I introduced about the droplet reaction and also as well as the droplet dynamics of gallium arsenide surface. So another question come by is that what will happen when the surface is really flat? And to answer this question, and then what I have done in my PhD is that I expose the outer flat silicon surface under arsenic flux. And let's come to have a look at movie here. And when the arsenic flux is open, and then it will form the nanostructure on the surface, as you can see here. And to some extent, this structure will be saturated. However, if I turn off the arsenic flux, and then the contrast of the surface will change, and finally the structures will disappear on the surface. So by LIM, and then we can observe the real-time process of the surface, and therefore with this capability, we can study different growth parameters to the surface. And first of all, what I study here is that I study the influence of the arsenic flux on the patterns. As you can see, at low flux, and then the surface will form various patterns, and then this is the hexagonal structure here. And with the flux increase, and then the structure will become smaller, but the density of the structures will increase. So furthermore, it will shows up here. So what I would like to say is that LIM gives us the capability to study the surface dynamics of 3-5 materials. And we obtain lots of information, and this is the information, and then resulting in some published and unpublished work. But the surface is really complicated, and there are still lots of work is ongoing. And for example, the anisotropic diffusion across the surface. As you can see here, with the temperature increase, and then the anisotropy increase, and also by cooling down the surface, and then we can observe the temperature-induced phase transition on the surface, and then study the phase transition dynamics. And this column shows us the process of the phase transition. Also, if we change the parameters like the temperature and as well as the surface flux, and then we can get the parameter space, and then finally we can plot the surface phase diagram, as you can see here. So, and this is, we are still understanding this is complex phenomenon, and then the result will definitely be published in the future. So here is the summary of my work. And first of all, I would say that gallium arsenide heterostructures are an important material system in modern society. And Lean is a unique facility which can make real-time nanoscale movies for surface growth. And Lean movies allow us to understand the complex growth process on surface. So I would like to thank my former group members, Professor David Jackson, Dr. Wenxin Tang, Dr. Xingqiu, and Dr. Changxi Zheng. Also some other collaborators like Dr. Jerry Tursov from USA, and also our Associate Professor David Paglin from School of Physics. And here is financial support in my PhD. And finally, I would like to say is the people in School of Physics, and for these people's contribution to create such enjoyable research environment. So, thanks.